This section of the text tells you about continuous propagation versus saltatory propagation. So, as you recall, an action potential is propagated or generated at the initial segment of the axon, and then it's going to move down the axon from one section to the other. This continues to the end of the axon, and it's called propagation. So, with two types of propagation, one is quite simple. The action potential moves from one section to the next nearby section to the next section, and so on. This occurs in unmyelinated axons, and it is pretty slow. Saltatory, on the other hand, occurs in myelinated axon, and this is because the nodes are depolarized, not the entire neurolemma. So it skips the inner nodes because the ions cannot cross when there's myelin, and it's much, much faster. A larger diameter axon will have less resistance to ion movement, so it will be faster. So this shows continuous propagation, where you have an action potential develops at this initial segment. So what we're doing is we're following an action potential from the initial segment on the axon hillock down the axon. So in this initial segment, an action potential develops, the membrane depolarizes, sodium ions enter, and sodium ions, because of the local current, are going to spread away from the gated channels and spread to the next section, and a graded potential has developed. The second section depolarizes, while at the same time this initial segment repolarizes. The graded potential spreads to the next section, segment 3. The second segment repolarizes, and so on. So the depolarization spreads down the axon step by step. But with saltatory, it's a little bit different. The action potential develops at the initial segment, and there's our sodium ions. These sodium ions spread along the inside surface of that membrane to the node. That node has been brought to threshold. An action potential develops at that node. The initial segment repolarizes, and from that node, a local current produces another graded depolarization at the next node, and so on.
Action potentials propagate in a continuous fashion in unmyelinated axons. Once an action potential is generated in the initial segment of the axon, it propagates the entire length of the axon. Recall that a threshold stimulus causes voltage-gated sodium channels to open. The influx of sodium ions generates an action potential. It also establishes a depolarizing current that flows to the next segment and brings it to threshold. Voltage-gated sodium channels open, regenerating the action potential in this segment of the axon. Current flows from this segment and depolarizes the next segment to threshold, thus regenerating the action potential yet again. In this way, regeneration continues in one direction all the way down to the axon terminals. The basis for unidirectional propagation is revealed when we take a closer look. By the end of the depolarization phase of the action potential, all voltage-gated sodium channels inactivate and voltage-gated potassium channels open. These two events render this segment of the axon temporarily insensitive or refractory to another depolarizing stimulus. However, voltage-gated sodium channels in the downstream segment are closed and receptive to a depolarizing stimulus. Thus, propagation occurs sequentially down the axon to the axon terminals. In myelinated axons, action potential propagation is a bit different. Here they propagate in a saltatory or leaping fashion. The myelin sheath consists of multiple layers of tightly wrapped glial cell membrane. But this sheath is not a continuous one. Exposed areas of axonal membrane, known as nodes of Ranvier, occur at discrete intervals. Voltage-gated sodium channels are abundant in the nodes, but largely absent between nodes. So, action potentials are regenerated at each node, not in areas covered by the myelin sheath. However, the myelin sheath does provide the insulation necessary for the rapid spread of depolarizing current. And the sooner the nodes reach threshold, the faster action potentials propagate along the axon. Saltatory conduction is extremely fast. Velocities often exceed 100 meters per second. In contrast, continuous conduction is fairly slow. Velocities rarely exceed 2 meters per second. Nevertheless, both continuous and saltatory conduction propagate action potentials over varying distances because action potentials regenerate along the way. Summary: propagation of an action potential. Once generated, the action potential propagates the entire length of the axon without decrement.
So you need to be able to understand and explain continuous propagation and saltatory propagation. Remember, if you can explain it to someone else, that means you really know it. What is the relationship between myelin and the propagation speed of action potentials? It speeds up action potentials. In which of the following is saltatory propagation associated? Myelinated axons.